Okay. Yesterday we talked about expected value. We said that expected value for the first moment is the average and is calculated as this. And we said that if we calculate the expected value of the function, we basically calculate this summation in the discrete form. And if it is the continuous, this is for the discrete notation. And if we want to use the continuous notation, how was it? The integral of gx fx dx. Now, let's do an example. Let's do an example. And the example is in this form. A random current I flows through a resistor with value of R to be 50 ohms. The probability density function of the current is, so the fx for the current is given as 2kx if x is between 0 and 0.5. If x is between 0.5 and 1, it is 2k, 1 minus x. Elsewhere, it is 0. A. Find the value for k that fx is a valid PDF. B. Find the expected value of the current I, and C. Knowing that power, the power which is consumed in a resistor P is equal to I square R, find the expected value of P. Find the expected value of P. So here we want to see what expected value means, how we can calculate it. So it will be a practice of this formulation. Now, as you can see, current is a random variable. It has a PDF. And now, as it is changing, we want to know what is the average value for this random variable for this current. So expected value will tell us what is the average But in order to solve that one, we need to have a clear form of fx. In other words, we should know what is the value of k. In order to calculate the value of k, do you have any idea how we can calculate it? Yeah, we know that the integral of fxx dx should be 1. What are the limits? From minus infinity to plus infinity. There are two ways to solve a question like that. One of them is this. Integral from minus infinity till 0. I am dividing my integral into the categories, which is mapping with the piecewise function that we have. From 0 to 0.5, I have 2kx dx. From 0.5 till 1, I have 2k 1 minus x dx plus 0.5 from 1 to infinity, whatever the function is. Now, can you tell me that what is the value of the function from minus infinity to 0 and from 1 to infinity? It is 0. So basically you should calculate these two simple integrals and equate it to 1. I am not going to solve this integral because when we have such a nice piecewise linear function, we can use geometry in order to solve it. How I am using geometry is this. Maybe pay a little bit of attention and then I will let you to write it down. Now, we know that everything is between 0 and 1. After and before that is 0. Which we don't care. Now, from 0 to 0.5, I have 2kx. Can you tell me that if I put instead of x 0.5, what will be the value? K. So this is k. So I am going up. And because it is linear, in the next term it has to go down like that. But we can always check. Put the value 0.15 here. It will be 1 minus 0.5, which is 0.5, and we get still k. 2 multiplied by 0.5 is 1. If I put 1, I will get 0. So it is a triangle, right? It's a triangle. Now, the formula says the integral of fx from minus infinity to plus infinity of fx should be 1. I know before 0 and after 1 it is already 0, so it means that it implies that the integral from 0 to 1 of fx dx should be 1. What is this integral? Yes, the area underneath the graph. This is a triangle. Area should be 1. It's a triangle. The height is k. So it's 1 over 2 multiplied by k, and the width is 1. So from here, I get that k should be equal to 2. K is equal to 2. This is easy if I have a linear function. If not, you have to calculate these integrals. Can you calculate the integral, or do you want me to calculate it for you to see how we can do it? Can you do it? It's simple, right? The result of this is kx squared. This one is minus k, that multiplied by 1 minus x squared. You put the values and you calculate. But if you can use geometry, always geometry is a great help. So if you want, you can write down this, then I will continue with the continuation. Okay, so let's write down our fx, how it looks like, by putting the new value for k. K was 2, so it is 4x. 4x is between 0 0 and 0.5. Then it will be 4, 1 minus x, when x is between 0.5 and 1 and 0 L squared. So part A is done. What we want to do, we want to calculate the expected value of the current. So we want to calculate the E of x, which the formula was saying that this is the integral from minus infinity to plus infinity of x, fx dx. Now, we know that fx is 0 if we are less than 0 or we are greater than 1. So it means that this integral will be broken into a very smaller integral. It will be the integral from 0 to 1 of x, fx dx. And because this is a piecewise integral, it means that we have to write it as the integral from 0 to 0.5 of x multiplied by 4x dx plus the integral from 0.5 to 1 of 4x multiplied by 1 minus x dx, which is the integral from 0 to 0.5, 4x squared dx plus integral 0.5 to 1, 4x dx minus integral 0.5 to 1, 4x squared dx. Right? What I have done, I multiply this with these two terms, and I also expand the integral. Now, the result of this one is 4 over 3 x cubed from 0 to 0.5 plus 2x squared from 0.1 to 1 minus 4 over 3 x cubed from 0.5 till 1. I put the values. 4 over 3 multiplied by 0.5 cubed minus, well, if I put 0, it will be 0, I don't write it, so minus 0, this is the first, plus 2 multiplied by 1 squared minus 2 multiplied by 0.5 squared minus 4 over 3 multiplied by 1 cube minus 4 over 3 multiplied by 0.5 cube. Believe me, if you do the calculation, you will get the result to be 1 over 2. You can test it. Check if my calculation is correct or not. So, this means that expected value of the current is 0.2. Is 0.5. It's 1 over 2. Now, the next part of the question asks, find the expected value of the power. The expected value of the power. For the expected value of the power, we know that P is equal to I squared R. which, what was the value of R? What was the value of R? 50? 50 I squared. So expected value of P is expected value of 50 I squared, which means the integral from minus infinity to plus infinity of 50 I squared, 50 x squared, because the random variable for current is x, fx dx, right? Similarly, we know fx less than 0 greater than 1, it is already 0, so we will derive the integral only between 0 and 1. So it will be 50 integral from 0 to 1 of x squared fx dx, which will be 50 integral from 0 to 0.5 x squared multiplied by 4x dx plus 0.5 to 1 of 4 x squared multiplied by 1 minus x squared dx. Which is 50 x to the power 4 from 0 to 0.5 plus 4 over 3 x cubed from 0.5 to 1 minus this is x minus x to the power 4 from 0.5 to 1. If you do it, you will get the value to be 14.58 watts, which is the unit of the power. You have to just put the values and do the calculation. But I want you to observe something. Can you tell me that 0.5 multiplied by 50, what is it? 25. Is it equal to 14.58? No. So it means that the expected value of x squared, 50 x squared, is not equal to, if we square this one, it will be 0.25 multiplied by 50, 2.5, 2.5 multiplied by 5, 12.5. This is not equal to 50 expected value of x squared. In other words, because this is also the mean of P, the average of P. So although P is equal to I squared R, mu P is not equal to mu I squared multiplied by R. We will see if you have some linear combination, some additional scaling of expected value, it will imply if the new variable is just simply a linear scaled version of the previous kind of variable, the same will have an expected value. But when we have some nonlinear operation like s square, we see that we cannot simply calculate the expected value by finding its square. We remember, if we have a very special case, which is if we calculate the expected value of x minus mu, if we calculate the expected value of x minus mu s square, what do we get? Variance of x. Variance of x. As an exercise, you may do this. Part D, calculate variance of I, which means that you have to simply use this formula. The only question is, what's mu? Yes, we already know mu, 0.5, 1 over 2. So this is mu of I, which is already 0.5 in our example. So you just put it in the formula and you use the same type of integration and you calculate it. Variance. Variance. What does variance represent? It shows how much separate the data is around the mean. So it talks about the shape of a function. I mean, variance is telling you how the shape of the distribution is in general. If we have the same mean, the same type of distribution, different variance will show different shapes. Can you tell me that which one has a higher variance, which one has a lower variance? Yes, this has a lower sigma, this has higher sigma. You know that for the sigma we have to compare it. If I give you a value for sigma, you cannot say if it's high value or low value in general. Sigma 25, is it high or low? We don't know. We have to compare it. But one of the things is sigma s square variance, or its square root, which is the standard deviation. It does not depend on the location of the distribution. What I mean is, remember our current example, okay? We had a current example. .5, 1, and this was 2, right? N plus 1, n plus 1 over 2, 2. these two distributions have the same variance. Because variance does not depend on where you have your function. It depends on the shape of your function. What about the mean? These two have the same mean. These two do not have the same mean. In other words, mean depends on the location of your function, whereas the variance only depends on the shape of the function that we have in our hand. Now, yesterday when we talked about the formulation of the variance, we said that sometimes it is easier for us when we want to calculate it to do this, to calculate which was the expected value of x squared minus s squared of the expected value. Let's prove it. Let's prove it. We want to prove this formula. In order to prove it, we have to go to the definition. What is the definition of this one? I start from the left-hand side and try to get to the right-hand side. This is the integral x minus mu squared fx dx. I don't put the I will put the index of x to understand what this is here. Now, this is a polynomial, right? I find them, I expand it, and I get integral of x squared minus 2 mu x minus plus mu squared multiplied by fx x dx. Are we all happy till this point, Professor? Yes? And this is equal to, now I am multiplying fx by each of this one, and I divide it into the three integrals. I get integral of x squared fx x minus 2 mu, because they are constant, I put them out of the integral directly, x fx dx plus mu squared integral fx x dx. I hope you understand that all the integrals are from minus infinity to plus infinity, right? You know that this is all from minus infinity to plus infinity. Now, what is the integral? Nasya, what is the integral from minus infinity to plus infinity of fx dx? This is 1. What is the integral x fx dx? This is the expected value of x, which is mu. What about this one? x squared fx dx. This is the expected value of x squared by definition minus 2 mu multiplied by mu is 2 mu squared plus mu squared, right? So what is the result? It is expected value of x squared minus mu squared. The proof is done. Proof is done. Now, in the example that we solved, we saw that when we are calculating the power was I square r, and I was a random variable. And we saw that if we calculate a square random variable, it doesn't mean that the expected value will be a square. But let's see some properties of these expected values. Now, do you have any question? Let's talk about a very important theorem. And then after that, we do an example. regarding to that theorem. And then we will talk about the general form of that theorem that I derived on the board. So the theorem says for a random variable x and a and b constant belonging to real numbers. You have a and b belong to real numbers. Then expected value of ax plus b is equal to a multiplied by expected value of x plus b. So this is a very important theorem. Which you need to know the proof. Now the proof is pretty simple because what we do, we use the definition of the expected value. Expected value of ax plus b is integral from minus infinity to plus infinity of ax plus b fx dx. Just expand the integral. A is constant, so it comes out x fx dx plus b integral fx dx. Now, you tell me, what is this integral? This is the definition of the x. What is this integral? 1, because it is an integral from minus infinity to plus infinity of PDF. So it will be a ex plus b. So the proof is pretty simple. And let's do an example which benefits from this theorem. And the example says let x be a random variable with mean 5. What is the expected value of random variable y if y is 3x minus 10 The solution is in this form. E of y is e of 3x minus 10, which is 3 e of x minus 10, which is 3 multiplied by 5 minus 10, which is 5. And the general form of this theorem, which can be similarly proved, is expected value of a gx plus b hx is equal to a expected value of gx plus b expected value of hx. This theorem says that if random variables are linearly combined, their expected value will be also linearly combined. The expected value will be linearly combined. Prove it at home. How to prove it? The same way that we already have done for the previous theorem. But we cannot say the same thing for variance. We cannot say the same thing for variance. For variance, if we are linearly combined, we do some linear combination to random variables that we have to see how the variance will be changed, which we will talk about it in few seconds. See what will happen if we want to calculate the variance. For the variance, we want to see that what is sigma square of ax plus b, right? And we know this is actually expected value of x minus mu squared, right? Do you like me? So what we need to do is this. Step 1. What is mu of ax plus b? Well, let's call this one y. It should be y. What is mu of ax plus b? This is a mu of x plus b. Do we all agree? We just prove it in the theorem. Then, by using 1, we get that the sigma of ax plus b squared is expected value of, instead of y, I put ax plus b, right? Minus, instead of mu of y, I put a mu x plus b multiplied by minus, it will be minus b. Right? Minus b's are cancelling each other. And plus b and minus b are cancelling each other. So I have expected value of ax minus a mu x squared. I factorize e. A squared multiplied by x minus mu squared. Now, from the previous theorem, we know that if a constant is multiplied by r term, I put the constant up, right? A is constant. So I will put it out. So it will be equal to a squared expected value of x minus mu squared, which is a squared sigma of x squared. So what we get is this formula. Sigma squared of ax plus b is a squared of sigma squared x. Now, we were expecting to see something like that because we said the variance does not depend on the location of the function. It depends on the shape of the function. So if you multiply a function with an scalar, we are expecting to see change in variance. But if you do some translation, nothing will happen. Instead of, in other words, sigma square of x plus 5 and sigma square of x is the same. The graph that I draw for you regarding to our current example. It doesn't matter where you put it, the variance or standard deviation will be the same. But if you are multiplying your random variable with a scalar, the variance will be multiplied by s square of that scalar. And this is the proof. We shall do several examples regarding to this linear combination of random variables, which we will do it in our next lecture. Do you have any question? If you have no question, this is the end of the lecture.